Yeah, I'll introduce Alex if you like. Yeah. Okay, our next speaker is Alex To from Overup and Partners in Hong Kong. Alex has got a lot of experience in using wind tunnels. He's responsible, or has been responsible, for Arab projects, many in the Asian region, including the Olympic Beijing National Stadium, the Beijing CCTV building, and Guangzhou Canton Tower, the Guangzhou East and West Tower, and so on. There's many more. So we're interested in hearing Alex's experience.
Thank you, Peter. Good afternoon. I'm going to talk to you about some full-scale measurement that we did in buildings in Hong Kong. Now, we do a lot of tall building design, and some of them are in Hong Kong. So the first question is, when we do our design, we do a lot of assumptions. When we do our design, we do wind tunnel testing. And during the analysis, we have a lot of assumptions. So how good is those assumptions? What is the real behavior of the building compared with what we have designed? So the initiative is we do some measurement and see how the building behaves. So what I'm going to share with you today is, first, I'm going to share with you what we have done, what we have measured. We have developed a new method to estimate the damping for the wind analysis. And also, I'm going to share with you a comparison between the wind tunnel test result and the full-scale measurement result. So the objective of this full-scale measurement is divided into two stages. So in the short term, we investigate the dynamic properties that include the natural frequency of the buildings, the damping ratio, and mold shape. And in the long run, we want to provide information to assess the actual risks or conservatism we have embedded in the wind engineering design process. This is the map of the Southeast Asia, focused in Hong Kong and Philippines. This is the white color is a diameter of 800 kilometers from Hong Kong. So I'm showing that is because whenever a typhoon is entering that white semicircle, we're going to have typhoon signal number 1 in Hong Kong hoisted. So everyone knows the typhoon is coming. When a typhoon is coming, what we are going to do is we're going to calibrate all the equipment, bring it to the site, set up the equipment, and then wait until the typhoon goes through Hong Kong. Collect all the data after the typhoon, and that's how we did the measurement on a number of, we can do a number of tall buildings measurement at the same time. This is one of the tall tower that we have instrumented. This tower is more than 300 meters tall. We have put some sensors on the building top. So you can measure X and Y acceleration. Basically, it's an accelerometer that can measure the building movement. That's another typical tower in Hong Kong, also over 300 meters tall. All these buildings are Arab designed, and we have wind tunnel testing. So in 2008, there's a big typhoon, Typhoon Nuri, attacking Hong Kong. So if you look at the path of the typhoon, the measurement shows that the gust wind speed is more than 100 kilometers per hour, and it's landed in Hong Kong. So the typhoon is hit directly on Hong Kong. And if you look at this graph, it shows the y-axis is the wind speed, and the x-axis is the time. So you can see clearly the typhoon eye in the middle, which is typical a typhoon track. There's another typhoon, HiQP, in 2008. It's also another quite big typhoon. The gust wind speed is more than 100 kilometer per hour. It didn't land in Hong Kong. And you can see, again, the wind speed vary with times, increase when the typhoon is close to Hong Kong, and then the wind speed decrease. So it's typical time trace. So if we look at the wind speed versus the acceleration, that's the measurement period for Typhoon Nuri, and also the measurement period for Typhoon HiQP. If you look at the acceleration response of the building, you can see a very well correlation acceleration with the wind speed, which is expected because larger wind speed give you a larger acceleration. This shows the first 3 mode of vibration of the building. So the first 2 mode is translation, and the third is torsional. And the frequency is 0.15 hertz. This graph shows you the frequency versus the acceleration. So the y-axis shows the frequency of the building, and the x-axis shows you the acceleration. So we plot the graph. You can see that plot the graph. You can see there's a trend with a sloping down trend line. So it shows that when the acceleration is larger, the frequency is smaller. And that phenomenon actually has been reported by many researchers, including Professor Tamura, which shows that when the building is deflected more, in that small range acceleration, the frequency actually vary with the building amplitude. That shows the damping ratio versus the acceleration for that building in that 2 typhoon. So the y-axis shows you the damping ratio, and the x-axis shows you the acceleration. If we plot, you can see the scatter of those damping, but if you look at the trend line, there's a slightly increase, but we don't know. We need more data to confirm that. Now, the damping ratio that we have measured, we use a new method. The traditional method to assess damping in wind engineering use random decrement method, which have a number of shortcomings, especially when we want to know the uncertainty of the results. So the method that we have developed is a fast Bayesian FFT method. This method has been documented in the Journal of Engineering Mechanics. What it does is it uses look at the wind data and look for the most probable value, and at the same time assess the posterior of the PDF, which in that way, not only you can get the most probable value of the damping ratio, but also you can have the COV, the coefficient of variation of that damping ratio. And that is very interesting and important. So if you want more detail about this method, you can refer to the Journal of Wind Engineering Mechanics. We try to compare what we have measured and what we have tested in the wind tunnel. So this is the one of the TopO model that we did for this project. Again, for the TopO result, we have different wind speeds from different wind direction, and this shows the polar plot. This graph here is a little bit small, but it shows the two events. One is Typhoon Nuri, and one is Typhoon HiQP. The most interesting, that shows the wind. The topmost graph shows the wind speed, wind direction, and the frequency of the building. Most interesting graph is that one. It shows the damping ratio versus the time history of the typhoon. So you can see the variation of damping. For every single point, you have a most probable value, and also you have a variation of this damping with time. So all these numbers are calculated in a half an hour non-overlapping wind or windows. So if you look at the trend of the damping, is a little bit smaller than 1%, which is close to our estimation. And also during the Typhoon HiQP, it shows very scattered data here. Again, the damping ratio is a little bit smaller than 1%. We want to check the building behavior when it is affected by monsoon also. So apart from the 3 typhoon measurement, we also do the monsoon measurement during last year. So this is the measurement results. Again, the damping ratio that we measure is very small. If you look at the high wind speed region here, the damping ratio is a little bit less than 1% or between 0.5 to 1%. Again, those winds are relatively small wind because we're talking about, say, less than 3-year return wind. We haven't had very big wind event yet, so we're waiting for the next big typhoon. This is the last graph that I'm going to show you. It shows the comparison of the field data and the wind data. So in the x-axis is the field identified result, and in the x-axis the wind tunnel data. So different colors shows different events. Say for example, the blue one showed the Typhoon Nuri, and the green one showed Typhoon Maggie, and the black is the monsoon event. So for the monsoon, the wind speed is much smaller, and you can see that the comparison between the wind tunnel and the field measurement is less satisfied. But for relatively big wind events, say typhoon, the blue dot and the red dot, they're more or less sitting in this line, which shows that the wind tunnel estimation and the full-scale measurement, they match quite well. And this is the left graph shows the mode 1, and the right graph shows the mode 2 comparison. Okay, so to conclude, we have used the fast Bayesian method to estimate the damping. We found that the frequency decreases with increase in acceleration levels. And we found that the damping ratio is less than 1% for super tall buildings at low amplitude vibration. And we also found that the wind tunnel prediction gives a reasonable agreement with the full-scale field measurements. So ongoing project, so we are expecting much stronger typhoon in the next few years, which can help us to understand the building behavior on long return period event. So we will continue measurement on those tall building and other super tall building. And we would like to know the damping for ultimate state design. So that will help us to design future tall towers. Thank you.
Well, thank you very much, Alex. We've got time for a few questions, although given your last conclusion that you found good agreement between the measured stuff and the wind tunnel, I'm not sure we should encourage questions. But yeah, I'll throw it open. Any questions out there? Professor Tamura? You have the microphone down to the front, please.
Thank you very much. A very interesting presentation. I have two questions about damping.
Yep.
You showed the scatter of damping and including the negative damping in the full-scale result. What is the reason of that? And another one is your new proposed technique. Seems to be based on frequency domain, right? And in that case, the frequency resolution near the natural frequency is very important. Otherwise, the 100% or 1,000% error can happen if you use a very coarse, not fine resolution was used. So I'm asking about the time history of the damping. In that case, the resolution can be very not so good, in my opinion. So how about the problem of the resolution, frequency resolution problem for that?
Right.
And two questions.
So the first question you're asking about the negative damping, right? So in the measurement, we measure the building movement. So it's the total damping of the tower. So if there's any negative damping, it's included in the result. Yeah. And the aerodynamic damping has been included. Yeah. And another question is about the frequency resolution. When we do the measurement, actually the data collected in a very high sampling rate, and it's taken for
sampling rate is not so important, and length of the data is necessary for the high resolution of the spectrum near the peak. It's related to length of the data, not the interval.
The method, the fast Bayesian method, to my understanding, is seldom used in wind engineering field. But it's a well-developed method in the earthquake engineering field. I think most earthquake engineer, they know about this. The beauty of using the new method is that it look at the equation of motion and estimate the damping in the framework of the equation of motion. So it is a more reliable and analytically justifiable method to estimate the damping. So maybe we could discuss later about the details.
Do we have any more questions out there? Yep, we have one there.
You're going to think I'm a broken record asking about curtain walls. Can you add to your list on your future work correlation of wind tunnel test cladding pressures to actual measured pressures at the building?
Yes, sure. Yeah. And also, I would like to encourage fellow engineer and to talk to client and do the full-scale measurement on your future buildings. I think that is very important to share those data among the engineer. And that help us to build more reliable and better building in the future.
Okay, if we have no other questions, we'll just thank Alex and back him up for his encouragement to do more and more field testing, because I think it's something that all of us within the wind engineering field agree is needed, and we ought to be pushing as hard as we can as a design community. So thank you, Alex.
Thank you.